Hey, Accelerated Algebra. Today we're going to do a little more practice with square roots and then talk about nth roots, higher powers than just a square root. Be sure that you're taking your notebook out and you're writing things down. We're going to start some problems here and then you're going to finish them up on your own and enter your answers into Schoology. For today, we're going to assume that all the variables are positive. So that simplifies our life just a little bit. I've rewritten these and separated out the perfect square part of each of the square root of 12 and the square root of 8. This simplifies to 2 root 3 times 2 root 2. Or you might have just realized that the square root of 4 times the square root of 4 has to be 4. So it's 4 root 6. So it's the same idea here. We're going to take out the perfect square part. 72 is divisible by 36. That's a perfect square, the biggest perfect square that divides 72. And we're left with a 2 in the not square part. 36 times 2 gives us 72. X is not a perfect square, but we can pull out y to the 4th and be left with just one y over here. And z to the 6th is a perfect square. So in your notes, I want you to simplify this part, and this part is going to stay the same. So you fill in that blank. When we have a radical in the denominator, we have to rationalize the denominator. So for this one, all you need to multiply by is the square root of 7. And why is that? Well, that gets rid of the square root of 7. Then square root of 7 times the square root of 7 is 7. So we would be left with the square root of 7 over 5 times 7. You simplify one more step. Here where we multiplied by the conjugate. And that looked a lot like difference of squares. So try to remember why we did that. The whole reason is when we multiplied 1 plus root 5 times 1 minus root 5, our new denominator is 1 squared minus the square root of 5 squared. But of course, that's just 1 minus 5. And in the numerator, we have to do distributing. So you're going to have to distribute out 3 times 1 minus root 5. I'm going to let you do that and do your final steps. Remember that when we have radicals, like terms must have the same radicand. So these are like terms because they both have the square root of 11. So I'm going to rewrite this as 1 times the square root of 11 minus 3 times the square root of 11. Well, what's 1 of something minus 3 of something? You fill in the blank. Okay, here these look like maybe they're not things that we could subtract, not like terms, but if we simplify, so I'm going to write this as the square root of 9 times the square root of 3, because that's a perfect square, minus 48 is 16 times 3, so I'm going to write that as the square root of 16 times the square root of 3, because that's a perfect square. So you simplify and subtract, and I think you'll see how that works. When we multiply, you really kind of want to multiply the regular numbers together and the square roots together. So I'm going to just write that as 4 times 2 times the square root of 3 times the square root of 6. And you might even get a little clever and realize that this is 8 times the square root of 3, and the square root of 6 can be kind of split up as the square root of 3 times the square root of 2. So what's the square root of 3 times the square root of 3? Well, that's 3, so you're going to have 8 times 3 times the square root of 2. This one you're going to have to FOIL out, but before I even do that, I might realize that the square root of 20 is the same as the square root of 4 times the square root of 5. In other words, 2 root 5. That'll save me a little work later on. So if I'm going to FOIL this out, I'm going to go first, outside, inside, last. There's not going to be as much simplifying as you wish here, but I know that root 5 times root 5 is 5. So that's going to be 5 times 2. That's going to give me 10. Here, we can multiply the things under the square root together. There's not any more simplifying that you can do there. This is a little bit new now, but it's going to be the same idea. And instead of trying to pull out perfect squares, this is a cube root. So that means I'm going to try to write things as perfect cubes. So x to the 6th times x is x to the 7th. This is the perfect cube part. And the reason why that is because I can write x to the 6th as x squared times x squared times x squared. 3x squared. So think about what that would mean to take the cube root of x squared times itself 3 times. Well, it's just like the square root. When we have 2 of them, we can take one out. Now we have 3 of them. So we're just going to take out an x squared times the cube root of x, because that has got stuck under the cube root. Let's do this 5th root together. Now you're going to have to think of things that multiply by themselves 5 times. So let's look at the perfect fifth root stuff. Well, you might realize that 32 is 2 times 2 times 2 times 2 times 2. 2 to the fifth. And then x to the ninth, I'm going to leave that as x to the fifth here. And then I've got left over here and x to the fourth. This is all my perfect fifth root part. So I'm going to have 2x, and then I have left over the fifth root of x to the fourth. Now, notice you've got to pay attention now to the index here. This is called the index, and means where I have a cube root. So I want to take out my perfect cubes. I know that 8 is 2 cubed, and I know 27 is 3 cubed, so that's a perfect cube. Obviously, y cubed is a perfect cubed. And then I can have an x cubed, and what am I going to be left with over here? Or you can think of it as an x squared over 1. If you want. Okay, let's take the perfect cube of all this stuff. Inside the cube root, all I have is that x squared. You could also write this as 3x times the cube root of x squared all over 2y. That would also be fine. So now we've got fourth root. So I'm going to look for things that are fourth powers. 16 is 2 to the fourth. And d to the eighth, of course, I could take the fourth root of that. And I'm just left with 1 power of d stuck under the fourth root. Think about how this part would simplify.